Hello everyone. This is Dr. Shubham Sahai. As Rick already mentioned, I'm an assistant professor in the Department of Electrical Engineering at IIT Kanpur. First of all, I would like to thank Dr. Rick Day for inviting me to give a talk in this ATAL FDP, and thank you all for joining this talk. Let me also turn off my camera so that we can save some bandwidth. Okay. The content of my talk today is reliable and legitimate device characterization using commercial TCAD simulators. So TCAD simulators is one of the most, I would say, popular way of characterizing semiconductor devices. Almost 60% to 70% of the efforts or research papers from India in the field of semiconductor devices are simulation based. However, the quality of these simulation based papers is not very great. I mean, that is what I'm telling you from my experience and as a reviewer, I guess. So as a reviewer, we review multiple papers in a year, and we find that most of these TCAD simulators or TCAD simulation based works, people do it without having adequate knowledge of what exactly is TCAD, how exactly it works, what exactly are the physical models that you have to invoke in a simulation, and what exactly is the validity of your TCAD simulation results. I mean, TCAD is like, I would say it's a numerical solver, it's a mathematical solver. You give it any input, it will definitely output something. So if you're giving it a garbage input, or which is not at all relevant to your device, it will definitely give you some result, but that result itself would be a garbage. It won't be legitimate. So in this talk, I would be telling you the practices, how to make your TCAD simulations more reliable, more legitimate, so that reviewers can believe it, and so that you can publish more papers, or so that you can analyze more semiconductor devices. So as I discussed, first of all, I would like to give a brief overview of what I would cover in this presentation. So I would first cover why exactly do we need this device characterization. Then I would introduce TCAD, how exactly it works, what exactly is its flow. I mean, I would be taking a specific example of Centaurus TCAD, but almost all the commercial TCADs, they have a similar tool. So if you understand this, you won't find difficulty understanding the other tools as well. Then I would talk about the reliability of TCAD simulations, how reliable they are, and how can you make them more reliable. That is main concern of our talk today. Then what exactly is the role of device physics or physical models? Do we need to know all the device physics of the device which we are going to simulate, or we can neglect some of them? Then most important part of device simulation, which is model calibration, and which enables you to validate your simulation results. So first, what exactly is device characterization? So an experimentalist, he would simply fabricate a device. So if an experimentalist is fabricating some device, the next step is to find out whether the device he has fabricated, it's working fine or not, or whether the purpose for which he fabricated a device, it's solving that purpose or not. So first, fabrication is done, and then it is followed by electrical characterization. Now, electrical characterization simply relates the terminal voltages or currents. So what exactly do we do in electrical characterization? We use a probe station. We basically fabricate devices on a wafer. So those wafers are transferred onto a probe station. There we have some probe needles. We kind of probe the appropriate electrodes, and then we use something which is called a semiconductor parameter analyzer. The most common ones are Keysight's P1500, or even like 4200, Keithley's 4200 is also there. So these are some of the semiconductor parameter analyzers. So they contain something which is called SMU, or sense measure units. So by sense measure units, what they do is they kind of apply some voltage and they sense the current or the voltage out of that device. So that is what is done in electrical characterization. And what we end up having is we end up having the macroscopic behavior of the fabricated device. What do I mean by macroscopic behavior? We end up getting your current versus voltage relationship, your transfer characteristics, your output characteristics, S parameter measurements if you are doing some RF measurements, or CV characteristics if you are doing some frequency measurements. So because of this electrical characterization, we can have a relationship between the currents or the voltages at the different terminals of the device or at the different electrodes of the device. However, what this electrical characterization doesn't give us is device physics. What exactly is happening inside of the device? We are just able to see the relationship between terminal voltages, currents, and capacitances. What about other things? I mean, why exactly is the device giving such a result? what exactly is the physics governing that? So that is only obtained when we can, probe into the microscopic characteristics. What are those microscopic characteristics? So those microscopic characteristics can be electric field inside your device, it can be the doping concentration at different points in your device, the carrier concentration, and so on. So, these electrical characterization does not provide us any information about the microscopic properties. And in order to do that, we have to go for some alternate techniques. And TCAD is one of the efficient ways in which, we can analyze the microscopic behavior. So what exactly is TCAD? TCAD stands for Technology Computer Aided Design. So they simply facilitate measurement of microscopic properties. What are those? So as I previously mentioned, you can measure the electric field profile across a device. You can measure the potential profile. You can measure the carrier distribution profile at any point within the device, and so on. So that is what you can do with the help of these TCAD tools. Now, the TCAD also helps to understand and explain the underlying physics. How? Once you know about the electric field profiles, once you know about the band alignment of the device, once you know about the profile of the energy bands in a device, the potential profiles, where exactly the potential drops much, how exactly is the carrier profile distributed. Once you know about all these factors, you'll be able to explain the underlying physics behind the operation of the device. So, if you get characterized results from electrical characterization, I mean, you get, the ID versus VG characteristics or the transfer characteristics. Now you want to explain why we get this transfer characteristics only from the device. Then we have no other alternative than to go ahead with TCAD simulations. And not only this, it can also be used for predicting the performance of new architectures, such as those with new geometry or new inherent device physics. For instance, let's say we have a MOSFET, but now the MOSFET doesn't work, or I would say the Moore's law saturates after scaling your devices beyond 7 nanometer or 5 nanometer or 3 nanometer technology nodes. So what happens is we have to come up with new architectures. So earlier we used to have planar MOSFETs. So below 14 nanometers, or like beyond 14 nanometers, I would say above 14 nanometer technology nodes, we had planar MOSFETs. Beyond that, I mean, we came up with FinFETs. Till 7 nanometers, even FinFETs were working fine. So FinFETs are like 3D architectures. And then moving ahead for 5 nanometers or 3 nanometers, different companies are calling it by different names, but what exactly it is it's simply a nanosheet transistor. So some people call it by multi-bridge channel. So Samsung calls it by multi-bridge channel FET. Nanosheet is coined by IMEC and IBM. And then, recently Intel, also told that it could be used for its 2 nanometer technology node, and they called it a ribbon FET. So the names are different, but the architecture is, simple. It's a 3-dimensional architecture. You have several channels stacked on top of each other. So, TCADs are effective tools even while understanding the performance of these new architectures. So fabricating these devices is a very costly affair. And it's also, it also consumes a lot of, real estate, or I would say a lot of money. So what people do is, people first, simulate these structures, these new advanced architectures, and then depending upon the simulation results, they think whether to go ahead with the fabrication or not. Because money and time is something that, people want to conserve always. So TCAD helps you in that. So that is the role of TCAD in the industries, in the semiconductor industries. As I told that they are quite fast and inexpensive compared to experimental measurements. And that is one of the reasons why, before fabricating any device, people go for simulating it. And it's a good practice also. Even in your, academic institutes, you should first go ahead and simulate the device. You should also simulate its process, how exact process flow and all, so that you can see, whether the process steps or the recipe you have, defined for this structure, whether that will work fine or not. And also you should simulate, the device characteristics in the TCAD before fabricating. So that way you will save a lot of time as well as money. So these are the two prime factors which govern any industry or even the research. So that is what I was saying. So fabricate only if the simulation results are promising. Yeah. Okay, so that was, about application of TCAD or usefulness of TCAD. But again, whenever you are doing something with TCAD, there are certain things which you have to be very careful. So now some of the words of caution on TCADs. So TCAD is, like a black box. You give it some input, you get some output. This black box is configurable. I mean, you can configure this black box by defining appropriate model parameters, by defining appropriate solver techniques and all those things. But it's like a black box. It's like a computer. It hasn't got any brain of its own. Whatever you give it as input, it will generate some output corresponding to it. And in the beginning also, I told that if you give a garbage input, it will also generate some output, but that output will also be a garbage. And how to classify whether that input is a garbage or not, that is the main concern or main theme of this talk. So accuracy of any TCAT tool kind of depends upon the set of physical models used. I'll discuss in detail what exactly are the physical models, but physical models form the essence behind any TCAT simulation. So first of all, the user needs to be aware about all the physical models which can affect the device performance. For instance, let's say we are using MOSFET. So in a MOSFET, you know that the carriers are flowing close to the surface in the on state, right? So in the inversion layer, which is a very thin layer, the carriers flow close to the surface. And also, from a fabrication point of view, that whenever you make a surface, it has to contain, or it contains defects, or it contains some roughness. So because of that surface roughness, because of those defects, the mobility of those carriers at the surface is not as smooth as it is in the bulk. So there comes something which is called surface recombination velocity. So you have to consider this surface recombination in your TCAT in order to model your MOSFET perfectly. Apart from that, there are several other models as well, like SRH. There are other models which you have to include depending upon the operating conditions of the device. For instance, if you're operating the device using very high drain voltage, then your velocity, like carrier velocity, will be saturated. So to take that into account, you have to use a velocity saturation model. Similarly, if you are applying heavy electric fields in the perpendicular direction with the help of your gate electrode in a MOSFET, then you have to include something which is called perpendicular mobility degradation model, or the Lombardi model. So you have to be aware about the model files or the physical models that are available in the simulator and the physics of the device. Only when there's a proper match between the physical models that are present in the simulator and the device physics of the particular structure that you're going to simulate, then only you can say that your TCAT will give you reliable results. Now, what about these physical models that are present in the TCAT? Are they always going to give you reliable results? Answer is no. Most of these physical models which are available in the simulator, they consist of parameters which are calibrated to some experimental data. So the default value of these parameters, most of these physical models are empirical. They have some fitting parameters, and those fitting parameters are kind of calibrated to some experimental data. However, those experimental data may belong to some 1990s or 1995s, where the device dimensions are pretty large. So if you go ahead and use the same set of device parameters, even for the modern devices like 7 nanometer device or 5 nanometer device, you are not sure whether you will get exactly the results which you obtain experimentally. So that's one reason why you have to calibrate your parameters or tune your parameters again, even though the set of physical models that is available in your simulator is already calibrated to some experimental data. So that is what I was telling. Using default parameters does not ensure that the simulation results are precise every time. For new devices, physics can be different, phenomena can be different, and as such, experimental conditions can be different. And as such, you have to reproduce those experimental conditions by tuning your default parameters to match the experimental data. So this process is known as calibration, and this is very important to validate the simulation setup. I can go to the extent of saying that without calibration, all the TCAT results are shit, or they're of no use. Now, what exactly is calibration? So calibration is the practice of tuning the model parameters of different physical models available in a TCAT to match the simulation results with an experimental data utilizing the same experimental results in the simulation. So this was just a definition. Let me explain to you clearly. So what exactly happens is you obtain some experimental data, or you see some experimental paper which is already been published, or you get some experimental data from some of your groups, or when you fabricate a device. So you kind of make the same device structure in the TCAT. You kind of reproduce the same device structure in the TCAT. You use the same gate length, same gate width, same oxide thickness, everything same as that, what you have obtained in your experiments. And then you try to analyze the behavior of this same structure which you have kind of copied in your TCAT by running simulations. Now, once you run the simulations, you get some output, and then you try to compare these simulation results to the experimental results that you obtained via electrical characterization. And then it's an iterative process. Once you get that data, then what you do is you try to tune the model parameters of these physical models, and then you try to match the experimental data with your simulation results. However, a word of caution here also, you cannot use any arbitrary value of these model parameters. For instance, if you are working with tunneling mass of electrons or tunneling mass of holes, typically it's given in terms of m naught, which is the typical mass of a free electron in vacuum. So typical values are close to 0.4 m naught, 0.5 m naught, 0.1 m naught. So what if our results are not matching when using parameter values from 0.1 m naught to 0.4 m naught? Can you use a value which is like 100 m naught? Definitely no. So whatever model parameters you are changing, those should also be within some real limits or within some physical limits. It cannot be any arbitrary value. And these things will come only with experience. Or I would say, once you are very thorough with your theoretical study, then only these things you will understand very clearly. And this model calibration, as I told, it should be a prerequisite before predicting the performance of a new architecture using any TCAD simulation. So calibration is something that you need to do always before doing any TCAD simulation or before going for any TCAD simulation based study. Now with that, let us look at the TCAD tools which are available in the market, the commercial TCAD tools. So one of them, which is most commonly used, is Synopsys Centaurus. And I'll be talking more about this because this was kind of very close to my PhD thesis. I worked on it for 3 years. So I'll be talking, I have a huge deal of experience of working on it. So I'll be talking about this one. Second is Silvaco. So Silvaco Atlas is also a very, it's also a very popular tool. So earlier Silvaco Atlas was more popular, but since Synopsys introduced the 3D simulations and some of the physical models that Synopsys introduced, they are better, or they are much more widely used as compared to Silvaco Atlas. However, the tool flow between the two remains the same. Then there are other tools which are emerging, like this GTS TCAD, which is from TÜV Group in Germany. So this TCAD has also got some Schrödinger-Poisson equation solvers for some, I would say, NEGF calculations. So once you reduce your dimensions below 10 nanometers or 7 nanometers, you have these classical simulations which you can perform using Synopsys or Silvaco. These are not much relevant, and what you should do is you should go ahead with NEGF based simulation or something, and that is also available with this GTS TCAD. However, in the recent versions of Synopsys, they're also incorporating those models. So almost all the simulators nowadays, they come with some good NEGF solvers or some I would say quantum correction models are also there. So you can even use them for simulations of devices below 7 nanometer technology or 5 nanometer technology. Also, there are some freely available tools like this tool which is available on nanohub.org. So here you can just give the kind of parameters which you want to the device parameters, as in the device length, the thickness of everything, and then it simulates and gives you the result. So this is an online tool which is available for free. Any one of you can make an account on nanohub.org and use it. Also, this TCAD tools, apart from the commercial TCAD tools, industries also have their own proprietary TCADs. For instance, IBM has a proprietary TCAD called FieldBase. Global Foundries also has some proprietary TCAD. So all the industries also use this TCAD, but they are also very cautious while using this TCAD. They do not just input anything and then see the results. So how exactly do these TCADs work? I mean, what exactly are TCADs? How do they work? So TCADs are nothing but mathematical solvers. So they just solve some mathematical equations, some differential equations, some difference equations. That is what they do. However, by the means of this solution of these equations, it mimics the electrical behavior. And what those equations kind of represent? They represent the physical equations which govern the carrier profile, the conduction mechanism, and so on. So any real device which you want to simulate, it gets converted to a virtual device in a TCAD, whose physical properties such as doping is kind of discretized into a number of mesh points. So what exactly happens is, you have a device which is a real device. Now you solve in a TCAD these physical equations, not over the entire device, but you discretize that device into a number of points or number of grids or nodes, and you solve the equations only on those nodes or grids. The way you define those nodes and grids, that's unique to all of the simulators, but you can define these grids or nodes according to your wish. I'll also explain how exactly you can, have a proper choice of defining these nodes and grids when I go ahead. But any continuous device is kind of represented as a finite point of sparse mesh points. I mean, why finite? Because if they were infinite, I mean, any device is continuous. So in between any 2 points, there are like infinite number of points. So if you go ahead and solve, the equations on all of those points, it will take forever. So time is also a constraint. And just to save time, we just discretize any continuous device into a finite number of sparse mesh points, and then solve these equations only at those mesh points. For instance, this MOSFET over here, what we do is we kind of, discretize this MOSFET into number of these mesh points. So these are nodes. I mean, these points are nodes, and you can see that they're connected by, some triangles. So you can see several triangles in this device and several number of these points. So it is only at these points where, the physical equations are solved. So what are those physical equations? So one is Poisson equation, which relates, your charges to your potential profile in a device. Then you have electron and hole current continuity equations. There can be band-to-band tunneling equations. There can be other equations as well, depending upon what exactly is the physical phenomena that is occurring in your device. So what exactly happens is, at each of these points, these equations are solved self-consistently in an iterative fashion. And then whenever convergence is achieved, that value of voltage, that value of doping and all those things are fixed for that particular point. So that is how the TCADs work. That is how these simulations are performed in a TCAD. Also, in each iteration, an error is calculated. So what happens is, suppose I solve Poisson equation here at this node point and this node points. I mean, between two adjacent node points. And I find out that, the difference between the two, the difference between the potential of the 2 points is very large. So what happens is, I'll then solve current continuity equations. I'll find out the modified charge densities at these points. Then again, I'll solve Poisson equation. And then let's say the error between these 2 points reduces. So if it reduces below a particular value, which is called, epsilon error or something, if it is lower than that epsilon value, then we say that it's an acceptable value, and we can actually, use it, or we can actually the simulations then converge at that point. And this epsilon value or the error value also, it can be predefined, and we can actually it can be predefined, and we can actually also tune it. So that's the advantage that we have while using TCADs. Also, it's computationally very intensive. I would say the computational resources that a TCAD takes is quite huge. It's not very easy, and the computational intensity also depends upon the number of these, points which you define in a TCAD. So more the number of points, more the number of resources, more the processor requirement for solving these equations. And also they are not very fast. So 3D simulations such as which is shown over here, it may take even 2 to 3 days when you're running it on powerful servers. So it's not that fast, but still experiments will take large amount of time. Then bringing those wafers for electrical characterization, characterizing them, that also takes time. So it's faster as compared to electrical characterization, but at the same time it's slower as compared to your circuit simulations or compact models. I don't want to get into there, I don't want to get there, but it's slower than compact models and your circuit simulation. So that is what I wanted to bring. So what exactly is a TCAD's tool flow? So this TCAD tool flow is for Centaurus, but I'll argue that most of the TCADs in the market, they follow a similar tool flow. So what exactly happens is, first step is to create a device structure. In any TCAD simulator, the first step is creation of device structure. In Centaurus, it is done with the help of Centaurus structure editor. And what are the parameters that we have to define? So for any device, what we have to define? We have to define materials. We have to define geometry. That is whether the structure is rectangular or what exactly is the orientation of that, or what exactly is, how are these different materials aligned with each other and so on. Then we have to define the boundary conditions for the electrodes. Whether the contact electrodes which have been used here are these ohmic contacts, or these are Schottky contacts, and so on. However, there's another way of defining structure. We can also go ahead with process flow. So there are tools like S process in CentOS, where you can just define that, okay, like you make a recipe for realizing or fabricating any device. Similarly, you can define a recipe there. So the same process steps that you have defined in a experimental setup, you can actually go ahead and define it for even these process simulations. For instance, let's say I start with etching the wafer, so I can define the etchant, I can define the time for which etching is being done, even in the simulator. So it gives you such a flexibility. So that's what we can do with it. And generally, we use a simple structure editor to make these devices. However, you can also use this process S process. You can do those fabrication steps one by one and then come up with the structure. And now, once you have come up with the structure, then what you do is you kind of discretize that structure into different mesh points or into different nodes where you want these I would say physical equations to be solved. So that is done by a mesh generator, which is kind of very specific to CentOS, which is called SN mesh. Other tools also have some kind of mesh generators, and I'll discuss what exactly happens in the mesh generation and all, how exactly Delaunay triangulation is done and all in the later slides. Then we give this structure to a device simulator. So here it's a CentOS device simulator. So first we make the structure using S process or CentOS structure editor. Then we give it to CentOS device simulator or SDE. So what it takes is, it takes in as an input the device which we have kind of made using this structure editor. Then what are the other parameters that this device simulator requires? So it requires other parameters like the distance, the structure editor kind of gives you an output file in the form of a TDR file. So that TDR file kind of consists of information about different regions of the device, the materials used in the different regions, the doping of the different regions, and the distance between the consecutive mesh points. Now with that information, along with the definition of the electrical contacts, their location, this CentOS device simulator inputs it, and then along with that, what it also inputs is the information about the physical models that have to be used. I mean, what exactly are the physical models that govern the device physics of this structure, which we have kind of formulated using CentOS structure editor. Now we also have to define the initial boundary condition of the contacts, the mathematical solver to be used. For instance, these solvers, I mean, solution of these differential equations is very difficult. So the typical methods used are some iterative methods like Newton-Raphson and so on. So we have to also specify what kind of mathematical solver do we want, whether we want to solve the first, like whether we want convergence only for error or also for the derivative of errors and so on. And also, apart from this, we also want to input information such as what are the voltages or current values to which the different terminal or the different electrodes have to be ramped. So typically what we do is we create a structure and then we want to see its behavior, right? So we apply some voltage, check the currents, we apply some voltage, check the capacitances and so on. So information regarding all these things have to be fed into this device simulator. And then we also need to feed what exactly are the microscopic properties that we need to analyze. I mean, we may need to analyze electric field profile, the potential profile, the doping concentration at different points. Then also, we may need to analyze the band-to-band tunneling generation rate, the recombination rates, and so on. So depending upon the physical models that we are using and depending upon what we exactly want to perceive in this device or what we exactly want to analyze in this device, we also mention about the microscopic properties that need to be analyzed, along with all this information about the structure details, the electrodes, how what is the voltage that we have to apply to these electrodes, or what are the exactly physical models which govern your device structure, and so on. So apart from all these things, S-device also requires a parameter file. So what is a parameter file? So parameter file kind of contains all the default values of the parameters of these physical models. As I told before that the parameters of these physical models, they are calibrated to some experimental data. So there are some default parameters which are already present in the simulator, but we have to tune them in order to match the experimental data which are recent. So for that, S-device also takes in this parameter file as an input, and we have to change those model parameters in this parameter file, and then we can feed it to this Centaurus device simulator. So that is also one of the inputs which are given to this, Centaurus device simulator. As I told that these have to be matched to an experimental result, which is like the process is known as model calibration, before we can say that our TCAD simulations are validated or our TCAD simulations are even reliable. Now, depending after these, after getting these kind of information, the device simulator kind of solves those physical equations, considering these physical models and all these boundary conditions, the electrode voltages and all, and then what it outputs is a TDR file. We were discussing about what exactly this Centaurus device simulator gives as an output. So after taking these things as an input, what it gives you as an output is a TDR file. So what this TDR file does is, it contains the spatial solution of differential equations which you want to solve, and also a plot file, PLT file, which is also the format is .plt, that contains a relationship between the terminal voltages, currents, charges, capacitances, everything. So it gives you these two files. So TDR files, if you open the TDR files in a tool which is called SVisual, you can see how exactly is the distribution of carrier profiles, electric field, potential, electric field vectors at different location along the device. And if you open this PLT file, you'll find out how exactly is the variation of the input input voltages and the currents. I mean, you can see the output characteristics, the transfer characteristics, the CV behavior, and so on. So this is the typical tool flow of any TCAD. Here I've taken an example of Centaurus and told you all these things. So starting from the structure definition, we end up to a state where we can visualize all the microscopic properties and take informed decisions or explain the physical phenomena which are happening inside the device. Now let us first start with the first step, which is the structure specification. So what exactly are the parameters that we have to define during structure specification? So first we have to define region-wise geometry and the materials. Then we have to define the electrical contacts and where exactly are these located. Then we also need to provide the location of all these discrete mesh points and how they are connected. This is a very peculiar step, and this is the most important step while defining structure specification, because the convergence of your structure, the simulation time that your structure is going to take when you simulate it using device simulator, all those factors depend upon how exactly you have configured these mesh points. And you also need to define doping profile in the form of value at each of these mesh points. I mean, you just define doping profile for different regions, and then in that region, in all those mesh points, it will take that doping value to be the same or something like that. So you have different options as well. You can define Gaussian doping profiles, you can define uniform Gaussian, uniform doping profiles, and so on. Depending upon that definition, these mesh points get assigned to that, these doping values are kind of assigned to those discrete mesh points. Now this original device is kind of, as I told earlier, it is kind of emulated as a virtual device, which is discontinuous with discrete number of mesh points. And generation of these mesh points is actually crucial for device simulation. Number of mesh points determine the accuracy and the time for simulation. So this is the point which needs discussion. So if you have a very large number of mesh points, two mesh points are placed very close to each other. Achieving convergence of numerical solution or mathematical equation is quite easy when you traverse a very small distance or when your points are very close to each other. However, if the points are large, that also needs a large time for simulation, because now the physical equations are being solved at each of those points. So it kind of grows linearly with the number of mesh points. At the same time, if the number of mesh points is small, then the accuracy suffers, because then your device is being taken as not a continuous device, but as a very discrete device, I would say, where the 2 points are separated so far in the space that the value between the solutions at those 2 points may be very different. Achieving convergence in that case may be very difficult. However, the time that it will take for simulating such structures with coarse meshing, it will be very small. So there has to be a trade-off between accuracy, time for simulation, and the meshing. So this is what I was trying to explain. So yeah, there's a trade-off between acceptable simulation time, accuracy, and I would say the computational resources that are available to you. Because if you have large number of mesh points, that also requires a very huge RAM as well as a huge kind of processing capability. So the general practice is to construct dense mesh only in the regions where you obtain or where you expect high current densities. So in a MOSFET, in the channel region, you expect a high current density. In BJT, in the base region, you expect a high current density. And in the regions where you have high electric fields, such as depletion regions or tunneling interfaces, or in the regions where high charge generation is expected because of avalanche or because of any other factor. So you kind of make a coarse mesh for entire device, but you identify the regions where you have high current density or high electric field or high charge generation, and there you kind of use a very fine meshing, or use place these mesh points as close to each other as possible. Also, a general practice is to construct a dense mesh at all the interfaces, because an interface between two different materials, there like a large variation in the potential electric field is expected, and therefore we have to construct a dense mesh at all the interfaces. Now, as I told before, designing an appropriate mesh is the key to an accurate TCAD based analysis, and this should be focused on. Also, you have the I would say freedom to kind of specify the maximum and minimum distance between two mesh points along the device. So that you should use very judiciously. Once you have defined all these location of the mesh points or distance between mesh points in different regions, in different directions, then the simulator engine, what it does is there's a Delaunizer engine. So this Delaunizer engine in the meshing tool, what it does is it connects those mesh points in a triangular fashion by constructing acute angled triangles. Now the thing is, what happens if the points are located such that you cannot, connect them via acute angled triangles? So if the mesh points are such that it cannot be covered by, acute angled triangles, the mesh engine will connect them using obtuse angled triangles. However, it is those obtuse angled triangle points where, convergence will be very difficult to achieve. So you should always maintain your mesh, or you should always ensure that your mesh has like the points which can be connected using acute angled triangles. Now, the next step of device simulation, once we have defined our structure, the next step is device simulation. So, how we do it is it's basically a command, line thing. So we kind of generate a command file, we write a command file on our own, and then feed it to this S device. So the inputs of this command file is the previous structure TDR file, which you obtained from the previous stage, where we defined the structure and we got the final meshing and all. Then we input a parameter file, like I told, which contains the default parameters or the tuned parameters of the physical models. Then we also specify in this command file the output files that we want. For instance, if we want to see the structure, we have to specify that we want a TDR file. If we want to see ID versus VG or C versus V characteristics, we have to specify that we want a plot file as well. Then the name and initial boundary conditions of the electrodes, that also has to be defined. So name, as in whether it's a source, it's a drain, or it's a gate, or it's a emitter or a collector or whatever, or boundary condition. Boundary condition means whether it is a ohmic contact or it's a Schottky contact. So that is also very important to define. If you don't define anything, the simulator automatically considers it as ohmic contact. Then we also have to include all the physical models which are relevant for a particular device. And for this, we have to first analyze this device with our experience or with our understanding of device physics. We have to see in what modes of operation, what exactly are the device phenomena which may be relevant for this device. Once all these aspects of device physics are considered, like mobility degradation, how exactly the mobility will how exactly is the mobility behavior in the presence of these voltages, in the presence of these materials, in the presence of these artifacts of the device. Then the band structure, quantization effects, carrier transport, generation and recombination, including tunneling and including avalanche or impact annihilation as well. So these parameters must be first thought about by for the device which you want to simulate before including appropriate models for them. For instance, if you are working with tunnel effect, this tunneling becomes a very important phenomenon. There you don't worry more about mobility degradation. There you more worry about tunneling because that is a dominant mechanism. In a MOSFET, you worry more about mobility degradation, you worry more about SRH recombination. And at high voltages, you worry more about impact annihilation. So like that, you have to consider all the factors of the device which can be affected by this physical models, and then choose the physical models. Then, for instance, if there are devices in the if there are regions in the devices where the doping is larger than the density of states, then what happens? Bandgap narrowing is indispensable. I mean, if you have degenerate semiconductors, you have bandgap narrowing phenomena. So now the question arises: I know that there are bandgap that the bandgap narrowing phenomena is there in my structure, but now there are several models present in the simulator. For instance, there are Del Alamo bandgap narrowing model, Slot 2 bandgap narrowing model, and so on. how do we choose a particular one? So then we read about those physical models. We see how they have been modeled in the TCAD, and then depending upon their correlation with the exact physics, we kind of choose one. That is how we do it. Also, let's say if impurity atoms are present in the channel, that is if the channel is not undoped, but it's, let's say, doped to a high value, then there has to be impurity scattering. And once the carriers are flowing, there has to be carrier scattering. And also, if the impurity and the scattering centers, they're of opposite polarity, then there has to be a shielding effect as well. So now, how to include all these phenomena in our device simulation? So then you have to go to the manual, look at the physical models for mobility degradation. We find that Phillips Unified Mobility Model is kind of most comprehensive one in the manual, which kind of incorporates all these effects. So this is how the choice of a particular model has to be made. So you have to think logically and select the most kind of appropriate set of models from those available in the manual for the appropriate device simulation. Now we also have to include in the device simulation what exactly are the microscopic parameters which you are interested in. For instance, we are interested in knowing about the electric field profiles or the band-to-band generation profiles or the carrier density or the SRH rate. What exactly is it that we want to see at the end of the day after we are performing this simulation? That is also something that needs to be incorporated in this device simulation. Then what exactly are the terminal, what exactly are the electrodes for which we want to ramp up the voltage or current or anything else. So there are two kinds of simulation which are possible. One is your DC simulation or quasi-static simulation, which is you ramp your DC voltage and then you look at the current. And second is your AC simulation or the mixed mode simulation, where you ramp the DC voltage and on top of it you superimpose an AC voltage, and then you kind of get the trans impedance matrix, and then after obtaining that impedance matrix, what you do is you kind of extract the capacitance out of it. So in DC simulation, voltage or current is ramped in a quasi-stationary way. That is, there is no time dependence here. Whereas in your mixed mode simulation, there is a time dependence. You can perform transient simulations. Also, what this TCAD does is that it translates these electrical domain behaviors into mathematical domain solution, and then these voltages and currents are actually converted into some number which are provided as the initial conditions for solution of those physical equations or those differential equations. So that is what TCAD does. Also, we have to plug in the numerical solver specification. For instance, there are several numerical solvers which can solve differential equation. Some of them are Newton-Raphson, Gammel. So what exactly do you want? I mean, which kind of numerical solver do you want to solve these physical equations? So in general, what people use is a fully coupled or Newton method. And then you self-consistently solve Poisson equation along with the continuity equations. And from your information or knowledge about mathematics that whenever you are invoking Newton method or Newton-Raphson, it requires an initial guess, right? So that initial guess, how do we provide it? That also the simulator needs to know. Generally, what we do is we kind of extrapolate. So basically, what we do is initially we just solve Poisson equation. We get an initial guess, because solution of Poisson equation is relatively easy. And then once we have solved the Poisson equation and we have got the initial guess, then we invoke the continuity equation as well. And then we kind of taking that solution as an initial guess, we start solving Poisson equation and continuity equations in a self-consistent manner. Also, we can define the number of iterations per bias step. I mean, I told that first we calculate it and then we again solve it self-consistently. So there can be number of iterations per bias step. And also the relative error control, I mean, the difference between the error of the two nodes. That is also something that we can define in the math section while we are defining this device simulation command file. So these are some of the elements that we have to define. Now, by an example, let me tell you how to start simulations. So first what we do is we draw a rough sketch of the device to be simulated. Let's see, let's say that I have to simulate a double gate. I'm taking here a junctionless FET, not a MOSFET. So in a junctionless FET, the source, drain, and channel, they are doped to same doping level, uniformly doped device. So I have taken this just for simplicity because otherwise we'll have to define 3 different doping regimes and all. So here we have to define just one doping regime, and then we can share that between source, channel, and drain. Anyways, let's not go ahead in that. So we have taken a junctionless device, source, channel, and drain. All of them are doped to 10⁻⁹ per centimeter cube, doped donor concentration. My channel length here is 1 micron. So here I have written 1 micrometers. My gates, so this is a double gate device, so I have gates both on top and bottom. Then my channel thickness is 10 nanometers. My oxide thickness is 1 nanometers. My gate electrode thickness here is 1 nanometer. It's just for demonstration purposes. Actually, it's much more than 1 nanometer. It's close to 100 nanometers. And then there are spacers as well, which separate, the source and drain contact. And here I have taken source and drain contacts on top. I haven't shown here the coordinates of the, so source contact is taken from here to here till 25 nanometers. Drain contact is taken from here to here. And also the length is 25 nanometers on top. Now, what are these coordinates? So these device simulators, they take in, discrete mesh points. So we have to kind of, give the boundaries of these mesh points and the geometric shape. So what exactly define a rectangle? So a rectangle is defined by, it can be defined by coordinates of two extreme, diagonals or all the four sides. If you have coordinates of all the four sides or the extreme diagonals, you can define a rectangle. So what we exactly have to do is we have to specify the coordinates in these TCAD simulators. So first, we have to mention all the coordinates very clearly in the rough sketch. And typically, the left end of the device, that's taken as the origin. So here I've taken this as the origin. So everything on top of this is negative and everything on the bottom of this is positive. So this convention is opposite to that of, the Cartesian coordinate system. In Cartesian coordinate system, everything on top is positive, everything at the bottom is negative. But in simulators, typically how they work is everything on the top is negative, everything at the bottom is positive. So you have to, define all the important points of this structure, of this rectangle, specifically, the corner points of the diagonals or all the edges, all the coordinates of the edges. Once you have done that, let us go ahead and, look at a sample code, how to, generate this structure in CentOS SDE, device editor. So first, let me discuss about the section 1, which is, very important thing, which tells you the overlap resolution. For instance, while designing or while writing the codes, it may so happen that, inadvertently, you have defined a region and then you have defined another region which kind of overlaps with it. Now the simulator doesn't know what exactly it needs to do with that kind of a code. So here we have to, specify that. So here the kind of overlap resolution that I have used is mu replaces old. So let's say I defined this, channel first, and somehow I gave the wrong coordinates for drain, and the drain now starts from here. It kind of overlaps half of the channel. Then with this kind of resolution, that is new replaces old, the drain would be kind of, replacing the channel in this kind of region. However, if we go to old replaces new, or, like new doesn't replace old, then we'll have the channel and the drain will be created only where, the channel is not there. So this kind of overlap resolution are kind of given here. And this is simply a code. ABA is the code, how to kind of, implement this new replaces old kind of a overlap resolution. Now let us discuss about how to create these regions. So let's say we want to create the silicon region. That is, we want to create this active device region, source, channel, and drain. So first, we define, the location of the corner points of these. So we have to create a rectangle. This is the first, this is the first coordinate, which is origin. So here I've also mentioned the Z coordinate. However, this is a 2D structure, so we don't have any Z coordinate. So when we don't have any Z coordinate, the device or the simulator automatically takes it to be 1 micrometer. So what it simulates is for 1 micrometer thickness or 1 micrometer width in the Z direction. So here, what exactly is the silicon region? So it starts, so one of the coordinates is 0, 0 origin, and the other coordinate, the diagonal coordinate is 1.08 and 0.01. So all of these dimensions are in micrometers. So this is 1 micron, 18, like 1080 nanometers. This is 10 nanometers. So you just have to multiply by 1000 in order to convert this to nanometers. And typically the tool understands the language of micrometers itself. The unit is micrometers, not nanometers. So you have to convert every dimension into first micrometers and then define it here. So here my silicon, so this region, entire region is silicon. The active device here is silicon and it's stretching from here to here. So we just have to define its corner points. We define 0, 0 to 1.08 and 0.01. And then we define it as silicon and we name it as region 1. Similarly, if we have to define the bottom gate oxide, we'll just take the two, first we'll define that it's a rectangle, then we'll take the two opposite coordinates. So it's 0.0401, which is here. And then this coordinate is 1.04, 0.01. So, and then we define that it's SiO2 and we name the region as region 2. Similarly, we can make it for top gate oxide layer. We just define the opposite diagonal elements. Then the gate polysilicon layer, we just have to define that it's a rectangle. Then the one coordinate is 0.04 minus 0.002, which is this. Other coordinate is this, which is 1.04 minus 0.001. And then we define it as gate polysilicon and we name it as region 4. Similarly, we define all the regions of this device. So here we have one silicon region, two oxide regions, and two polysilicon gate regions. So we have total of 5 regions. So here we have 5 regions, right? Now we go ahead and we we write about the doping specification. What exactly are the doping in different regions? So we can define this constant doping profile or a Gaussian doping profile. We can have several options. However, here, as for simplicity of demonstration, I have given a junctionless spec where the source region, channel region, and drain region all are doped to similar doping profiles, which is 10 for 90. So here I have defined a constant doping profile or a uniform doping profile. I have named that doping profile as constant channel doping. It's phosphorus and its active concentration is 1E90 or 10.90. Then again, I have to place this doping concentration in a region. So here I just defined the doping concentration, that is constant channel doping means it's phosphorus 1E90. Now I have to place this constant channel doping in the regions. Since our region 1 was silicon, which is the entire thing, now I have placed my doping in the entire region. So that is what we do. And similarly, since these gate polysilicon regions have to be doped heavily, I define the constant gate doping, which is boron, that is P+, and the doping concentration becomes 10 per 20. And then I again place them on these two gate polysilicon regions. So since there are two, so I have to place them twice. Now what I do is I define the mesh, or I define the spacing between those points on which we want our physical equations to be solved. So what I do here is, so these are the maximum and minimum spacing between the elements. So this is the maximum spacing of element in the X region. This is the maximum spacing of element in the Y region. This is the minimum spacing of region in the X direction. This is the minimum spacing of elements in the Y direction. So I have taken the maximum spacing as 0.8 nanometers in the X and minimum spacing as 0.1 nanometers in the X. So in X direction, in this channel refinement, what I have is the maximum meshing or the maximum distance between the points can be 0.8 nanometers and the minimum distance between the points can be 0.1 nanometers. The best part about Centaurus device simulator is that, once you define interfaces, once you define different regions, what it does is in the bulk or inside this device or inside this region, it takes the mesh as the maximum mesh, and at the interface or close to the interface, it automatically takes the mesh or the distance between the points as the minimum mesh size which has been specified. So now I place this refinement in different regions. So I place it in region 1, which is my entire silicon device. Since all the active device behavior, all the currents, all of them are flowing inside this active device itself. So we have used a very fine mesh. For other regions like oxide and all, we can work with coarse mesh. So here for oxide, I've taken maximum distance as 5 nanometers, minimum distance as 1 nanometers. Then I've placed it in 2 regions, which I defined for oxide. Similarly, I've used the same kind of refinement for my gate polysilicon and I've placed them. Once I've done that, what I do is I have to insert the vertex for defining contact boundaries. So you see that here we haven't defined vertices or edges for placing contacts. So first we are placing one contact at 25 nanometers. So here we'll have this 25 nanometer and 0. So now I place for drain also. So from here to here we have drain, and it's from 1065 microns to 1080 microns. So from here to here we have the drain, and also we place a source and drain contact at the bottom edge as well. So here also we have a source contact. Here also you have a drain contact. Now we have to declare these contacts. So if we define source, and this is RGB, basically it gives you a red color contact of source. This gives you a kind of green color contact of drain. This gives you a blue color contact of gate. And now we have to position these contacts once we have defined them. So now how to position that contact? So we define it using this define 2D contact. We find the edge ID and position it. So what happens is how Centaurus kind of places it is, once you have defined 2 vertices, let's say I have defined it as 0 and at 25 nanometers. If we specify a coordinate in between 0 and this 25 nanometers, then it will place the source contact on the on the line which connects this 0 to this 25. So that is why we take 10 nanometers, which is in between that, and we place it. Similarly, we place it at the bottom as well. Similarly, we place it at drain, and then we place contacts at the gate. And then what we do is at the end, we build this mesh. We kind of call this Delaunay triangulation mesh engine, which kind of connect these mesh points using what should I say? Using those acute angle triangles, and that is how it works. Now let us look at what exactly is the structure when we run this code in the simulator. So when we run it in the simulator, you see that the structure is translated here, and you can see that the blue gates are there. These red source electrodes, these green are the drain electrodes. So it kind of made all these things just by copying and pasting this code in this command line window. Now, how do we do device simulation? How do we go about it? So first, as I told, we try to identify all the physical phenomena which may affect the device behavior. Then we write the command file. So first, what we do is we input the files. So first, we input the grid file, which is kind of the device structure, which was kind of given by the previous step, which was generated by the device simulator. Then we give the parameter file. In parameter file, it includes default parameters as well as the parameters that we have tuned in order to validate our simulation setup. Then the output files. What exactly is that we want? We want the plot files. That is, we want to see transfer characteristics or the output characteristics. We also want to see the structures. So for that, we have to define these output files. Then the initial conditions on the electrodes. So we have these electrodes, source, drain, and gate, and these are initially biased to 0 volts. A caution that the name of the electrodes which you have defined here should be same as the name which you defined in the structure while specifying the structure. Otherwise, your simulations won't run. Then about physical model specification, which is the key part. So here we define physics, and in that different models. So here I have included mobility degradation models. I have included Phillips unified mobility model and the Lombardi model, which kind of considers the degradation in the mobility because of the perpendicular electric field. Then I've also used effective intrinsic density, that is band gap narrowing model, and I've used the old sawtooth model, which gives you correct results for junctionless FETs where the doping is 1E90. Then I've used SRH and Auger recombination models. Now, since it was defined as the material of gate was polysilicon, you can also define it, you can also define an appropriate work function. I can actually define work function of 5.1 here. Then we have to define what exactly are the microscopic parameters that we want to plot. So here I have plotted electron density, hole density, currents, quasi Fermi levels, conduction band energy, valence band energy, conduction current, band gap, electric field vector, electric field in the direction of the current, electric field in the direction of holes, then potential, the doping profiles, space charge, the SRH recombination rate, the electron and hole mobility, the electron and hole velocity, donor concentration, acceptor concentration, tunneling rates, electron barrier tunneling rate, hole barrier tunneling rate, and so on. So you have the option of defining almost all the microscopic parameters that you want to analyze. Now, how do we define numerical solver? So it goes under this math section. So here first I have defined extrapolate. So what this extrapolate does is it's used for finding initial solution. So what it does is, depending upon the solutions of previous 2 iterations, it kind of extrapolates them to generate an initial solution. Then derivative simply means that in the Newton-Raphson, you have to kind of include the exact value of the derivatives of the RHS. Then you can also have this relative error control, where you can control the number of iterations for which one step or one bias has to run. Then here, the method that I have used is a block decomposition method, and the sub method is PARDISO. I mean, you can go through the manual for its discussion, but it's just the fully coupled Newton with block decomposition. That is what it means. Number of threads is number of multi-core processors that you can use for this simulation. Here I've used 8, so 8 means you can use 4 processors for running this simulation. Then this CNOM print is a very effective tool. What it gives you the maximum, it gives you the coordinates where your device is giving you the maximum error and what exactly is the value of that maximum error. Now, if your simulations are not converging, if you are using CNOM print in your math section, if you print, if you do the CNOM print for each iteration, it will print the coordinates where maximum error is there. So just by looking at the maximum error, you can rectify it. You can actually, in an iterative fashion, you can, let's say increase the number of mesh points in that region so that convergence becomes easy. So this is a very effective tool in, bugging, I would say debugging your simulations. Now the solve section, how exactly do we, mention what exactly are the voltages or currents that we want our device to go. So here we go ahead with solve, and then this is the init one is kind of the plot file. Then first, as I told, we go for initial solution. For finding initial solution, we only solve Poisson equation. So here, this is it. We want 100 iterations, or within 100 iterations, we want the solution. And we want to only solve the Poisson equation for initial guess. Now, we want to solve both Poisson, electron, and hole in a coupled way. So we write coupled Poisson, electron, hole. And then this is the plot file or the PDR file, which will store the values of all these microscopic parameters. Then we go for quasi-stationary ramping of our voltages. And here the goal is to first ramp the drain voltage to 1 volts. And here we also need to define the step of increasing of these voltages, the max step and the min step. So what happens is you start with 0 volts because that was the initial condition. Then your device, the simulator solves it for 0 volts. Then it increases the voltage by 0.001 volts. Then it starts solving it. And then if it converges, it again starts to increase the step size by 2 times, and it can go till 0.1. And similarly, if the device is not converging, if the simulations are not converging, the step size will reduce by a factor of 2 every time in all the iterations till it reaches a min step of 1e minus 7. If it doesn't converge even then the simulation will be stopped. It will just skip it. So first we ramp the drain to 1 volts. Then again we solve coupled Poisson, electron, and hole equations, like Poisson equation, electron continuity equation, and hole continuity equation. And then we ramp the gate voltage to a voltage of 1 volts. Here also we have to give it some steps, like the step, like initial step size, and then the max step and the min step. And then we have to end this by writing coupled Poisson electron. So by doing this, we kind of simulate it, and we go ahead with plot files. We get the plot files which are present in this init_1, and we get the structure file which is present in this under this name. So we then open SVisual, and then we see what exactly it looks like. So this is the structure after simulation. So you can actually make a cut line here, and then you can also plot the band diagrams. Here I've plotted the AC and EV. So here you can see that there is a huge overlap between the connection band and the valence band. So there can be band-to-band tuning also here. And here it shows you the ID versus VG characteristics of the device which we simulate. So we can visualize all these things. Now let me come to the most important part of this talk, which is model calibration, which I have been focusing so much. So as I told initially also, TCAD software is a numerical solver. It's a mathematical solver. It just solves some differential equations. It doesn't have any brain of its own. You give it an input, it will just give you an output. Can we validate if the results are accurate? And if yes, how do we ensure that our simulation setup is always valid for all the devices for simulating everything? So answer is model calibration, and it's the first step that has to be carried out before starting any device simulation. And what it does is, or what we do in it is, we kind of reproduce the experimental structure in the TCAD, and then we include some model parameters, we tune their parameter values, and then we try to replicate the experimental characteristics, electrical characteristics, with the help of our simulation results. So it's most tricky, and I would say it's very difficult part of any TCAD simulation based study. Because what makes it so difficult? So first part is it's very difficult to obtain all the dimensions just by analyzing the TEM images of structures. So most of the experimental papers, they only provide with TEM images or SEM images. So from there they'll just mention in the corner one dimension, like 10 nanometers or 50 nanometers, or the scale basically. So from there it's very difficult to obtain the exact dimensions. Then second, when you are it's fabricating the devices, the doping cannot be uniform, because the process inherently is ion implantation. So your doping has to be non-uniform. So we do not know, we just know the doping dose. So in the experimental papers, you'll know about the doping dose and the dopant energy with which these dopants have been bombarded onto your substrate. So from there you have to calculate the doping, and this doping is not uniform in the device. Also, when you're fabricating it, there are some stress in the layers or materials, and inherently, whenever you are working with oxides, whenever you are depositing any dielectric, there has to be some fixed oxide charges or trap densities which are never reported, or it is reported sometimes only. I mean, unless it's some reliability kind of experimental study, the trap density or their location in the energy bands and all those things, ELTS and all is not performed, that is not a regular norm. So it's generally not reported. How can we go about it? So we have to make some very intelligent approximations. For instance, whenever you are having any device and you find out that what you are simulating has a transfer characteristics which is shifted. So it's following the exact behavior, but it is shifted from the experimental transfer characteristics. Now, once it's shifted, when does your transfer characteristics shift in a MOSFET? When you have fixed charges or when you have some charges in the oxide layer. So it is always a valid assumption to assume that there are some charges in the experimental structure, because they cannot avoid these charges. They can minimize it, but they cannot avoid it. So then if you want to tune your parameters, or if you want to calibrate in case you are finding a shift in the transfer characteristics, you can do that by introducing fixed oxide charges or traps in your simulations. And then you can tune the density of these traps or their location in the energy band in order to reproduce the experimental characteristics. So as I told, these are inevitable while fabricating any FET. Second problem comes with the geometry. So there are some, so when you are fabricating devices, you do not make them perfectly circular or rectangular or something. You intend to do it, but you can't do it. So what happens is you end up having irregular shapes such as oval or trapezoidal. Now most of the simulators, their meshing is it's triangular, like you are using triangular mesh lines to kind of connect 2 points. So if you have an oval shape or if you have a trapezoidal shape, definitely you will end up having some acute or some obtuse angle triangles during Delaunay triangulation. So reproducing such structures or shapes in a TCAD simulator is very difficult. And also because of introduction of those obtuse angle triangles, there can be some numerical convergence issues. So in that case, what should we do? We should approximate these shapes to the nearest regular geometric shape, such as circle for oval shape, rectangle for pyramidal shape. However, you have to be very cautious. The effective width of your channel, for instance, in the case of MOSFET, has to be same, even in the case you are kind of converting, a rectangular shape to pyramidal shape, or if you are using a circular shape for oval shape. Because the current which is coming out of any channel region or any device is proportional to its area of flow, right? Area has to remain same. So you have to choose the dimensions such that the areas are same. At the same time, you can approximate these, structures to their regular geometric shapes. And no matter how hard you try, there will be a mismatch between a simulation result and experimental result. Because no matter how hard you try, no matter even if you're fabricating the device yourself, you won't be able to get all the information about the entire experimental structure. Your fabrication environment can do some tricks. So no matter how hard you try, you cannot get all the information, and therefore there will be a mismatch between simulation results and the experimental results. And you can only minimize those mismatches. So let me give you an example of model calibration. So this is a nanowire gel FET, which is having this kind of, I would say kind of oval cross section. Only what we know is that the width at the center is 10 nanometers. Now, reproducing such kind of structure in TCAD is very tricky. So what you can do is you can approximate it by a cylindrical cross section, and then you calculate its area. So this is a TM image, and you can see that only the scale is given, that this is 10 nanometers. And this gate length is 50 nanometers. So you can obtain only these information from this picture, which will be usually available to you in experimental papers. Now what you can do is you can calculate the area by using this as a scale, and then you can approximate it as a cylindrical geometry with appropriate diameter of this cylinder. Yeah. So that is what you should do, and then you can simulate it using TCAD, and you see that I have done that. And so the main funda here is you have to approximate it by a usual, or I would say a regular shape, but you have to keep in mind that the effective width should be same. Now, since it's a junctionless FET, I used Phillips unified mobility model because there has to be ionized impurity scattering, because it's doped to very high levels of impurity. Then carrier scattering has to be there. Then because in a junctionless FET you have the ionized carriers, which are so here you have ND, right? So you have donors which are present in the channel region. So when they ionize, they give you positively charged ions, and the carriers that are there are electrons. So these scattering centers are kind of these donor atoms or ionized donors, they kind of act as scattering centers and they're positive. Whereas these carriers, which are electrons, they're negative, so they're kind of attracted towards these scattering centers. So what happens is, these electrons kind of cover these scattering centers, and because of that, the impact of these scattering centers on the other electrons, it's very low. So this shielding effect kind of improves mobility somewhat in junctionless FETs. So this phenomena also has to be included, and Phillips unified mobility model incorporates that. So I used it. Then also phonon scattering is something that is present in all the devices, so you have to include mobility for that. And Phillips unified mobility model, it kind of includes all these phenomena. Then in junctionless FETs, you have a very high vertical electric field emanating out of the gate electrode. So once there is a high electric field, there will be this Lombardi mobility model, which takes into account the surface roughness as well as the acoustic phonon scattering because of the perpendicular electric fields. Then, since we are talking about short channels, therefore the velocity saturation has to be there, and I have to use this Canali mobility model for including velocity saturation. Also, since I told that it's sloped to 10 power 19, we have to use this band gap narrowing, and also we have to use Auger and SRH recombination models. And since we saw that there is a overlap between the conduction band and the valence band over here, close to the channel drain interface, we have to use a non-local band-to-band tunneling model. Now, can we use the default models? So if we use the default models, we won't be able to reproduce experimental characteristics. I found it difficult to reproduce experimental characteristics. So what has to be changed? So first, we are using SRH model, and the doping is 10 power 19. In usual SRH models, what happens is the doping is close to for MOSFETs, the doping is close to 10 power 14 or 10 power 15. So there the carrier lifetimes are large. It's 1 microseconds. However, when your doping concentration increases to 10 power 19, your kind of tau max, or I would say your kind of carrier lifetimes, they decrease. So here I have used a decreased carrier lifetime for mimicking this 10 power 19 impact of this doping on the carrier lifetimes. Then I've also tuned this tunneling mass of electrons and holes in order to match the experimental characteristics. Default values do not give you the exact results. However, I have changed it only from 0.1 M0 to 0.4 M0 and 0.65 M0. I haven't changed it to like 5 M0 or 10 M0. That those are non-realistic. Those are unrealistic and they should not be used. Now, as I told that when I simulated with these model files, I was getting a characteristics which was like this. So it was shifted by the actual experimental characteristics by this much voltage. So then, as I told that inevitably all these structures will have some oxide traps and defects. So what I did was I kind of included the traps. So once I included the traps, then I could shift the transfer characteristics towards the left, and because of that I was able to match the experimental characteristics. So by doing all these things, you can see that this was the experimental characteristics that they have reported in their paper, and these lines are my simulation results, and these dots are data which I've kind of so what basically I've done here is I've kind of extrapolated data from here. How we do that? There are some tools, dedicated tools like WebPlot Digitizer. There you can use this file and extract all these points, and then you can find a CSV file, and then you plot that CSV file along with the characteristics that you're getting from your experiments. However, although it shows that for different diameters it's matching perfectly, not perfectly. I was just trying to kind of tell you the errors here. So it looks as if it's calibrated, but if you look at the subthreshold slope of these three, you'll find that the subthreshold slope is quite good as compared to the experimental characteristics. You see that there is a deviation in the subthreshold slope. So that is happening because I do not know precisely what exactly is the location of these traps in the energy band. And that is something which we can get only when we have the devices and we do DLTS measurements. So since I didn't have the devices, I can't do that. I cannot find it out. I just approximated, and this is fairly good bit of experimental calibration. So if you produce this result in front of any reviewer, he'll say that okay, your TCAD setup is kind of calibrated to this experimental setup. Now this is again one point which I want to make here, that once you are calibrating it, you're kind of calibrating your setup, or you're kind of validating your simulation setup to the experimental environment which was used for fabricating these devices. If the experimental environment changes, or if the devices change, this set of calibration is no longer valid. So if you calibrate for junctionless nanowires, You cannot use this for, let's say MOSFETs. You cannot use this for tunnel FETs. Once the experimental environment changes or the devices change, you have to recalibrate your models. So this was done without any quantum confinement effects. But if you have quantum confinement effects also, I mean, if you're working with dimensions less than 10 nanometers or 7 nanometers, then what happens is these quantization effects or quantum confinement effects, they become dominant. They first lead to a modified charge density in the inversion layer, which can be incorporated by using a quantum correction model in these simulators, which is called density gradient quantum correction model. Also, once your dimensions reduce below this 7 nanometers, the band gap of silicon changes. What happens exactly is there is a significant amount of sub-band quantization, and because of that, the tunneling process is restricted through the first sub-band of the conduction band to the first sub-band of the valence band, and not at the bottom of the conduction band and the top of the valence band. It is restricted only between the first sub-bands or the second sub-bands, depending upon the bias condition, depending upon the material, and so on. So because of that, the band gap also increases. Now TCAD doesn't take this into account. How we can take this into account? So there are some dedicated simulators like this Band Structure Lab, which is available on nanohub.org. There you just mention, there you just give the geometry, there you give the thickness, and it will come up with the E versus K plot. And from that dispersion plot, you can find out the effective distance between the first sub-bands, and then you can calculate the band gap, the increased band gap or effective band gap, I would say. Also, there are some experimental papers which represent that once the band gap, once the thickness of silicon reduces to 3 nanometers, it not only band gap not only increases 2.41 electron volts, but it also becomes a direct band gap semiconductor. Anyways, so what I did was I took these two phenomena into account, and I calibrated density gradient model and this band gap by reproducing results of this structure, where so this was experimental demonstration of ultra short channel, where channel length is 3 nanometers and channel thickness is 1 nanometer at the end of this V groove. So I tuned the model parameters to produce these results, and by simulating the same structure which I got in the experiments. And once I have calibrated all the models, now I can say that my simulation setup is valid for simulating junctionless nanowire FETs, even when the dimension goes below 7 nanometers. So now I'll go ahead with the conclusion. So TCAD is a very powerful tool. It's necessary to explain the underlying physics behind the operation of any device. It gives you an insight into the microscopic parameters such as electric field, potential profile, carrier density, doping profiles, which your experiments can't provide. However, as it is said, with great power comes great responsibilities. So as a user, it's your responsibility to use this judiciously. And what are the main points there? So using default parameters, your TCAD simulations are not trustworthy. Also, the results given by your simulator are legitimate if and only if your model calibration has been done. Also, the user has to be aware about the validity and limits of the physical models and the inherent physical phenomena which are present in any device before going ahead with TCAD simulations. Also, this thing which I discovered while doing my PhD, working with these device simulations for almost 3 years, and experimental work is something which every reviewer believes, apart from the person who carries it out. While a TCAD-based simulation work is something which no reviewer or no one believes, apart from the person who has carried it out. So with this thing in mind, you have to always consider that whatever simulation-based study you are going to do, no one is going to believe it until you give them appropriate calibrations and appropriate justifications and appropriate physical, I would say, physical justifications. So at the end of the day, I would just like to tell that please use TCAD cautiously when you are extracting any meaningful information with the help of these TCADs. Also, if you want to know more about quality of TCAD-based papers, you can refer to this recent paper which appeared in IEEE Transaction on Electron Devices, where they were actually trying to explain what are the kind of TCAD-based simulation studies which are acceptable or which are kind of legitimate, and what are those studies which are not relevant for or not very good quality results, I would say. So the references or I would say this in this presentation I have tried to pour in my experience which I gathered during my PhD, and I also wrote a book on it. So most of the part of this tutorial was from the book that I've written on junctionless FET, and also many parts of it were from the Centaurus device simulator, Because without going through its manual, you cannot arrive at the physical models. You cannot go ahead with the simulations. So thank you so much for your patient listening. Any questions, feedbacks, or suggestions are welcome. Thank you so much. Sorry, are there any questions?
Yes, sir. Hello, am I audible? Hello?
Yeah, you're audible.
It's Dr. Raghavendra. Sir, may I know the validity of one freeware, the scalp on simulation, sir? Have you heard about SCAPS? Yes, CAPS, yes, SCAPS.
CAPS, what is it? I mean, I don't know about CAPS.
Okay, it is again a simulated software. It is a freeware actually, developed by someone from Belgium, I think.
Okay, see, TCAD or any other simulation software, unless you do model calibration, its validity is questionable. Because any simulator is just a numerical solver. You talk about console, you talk about any simulator. It's just a numerical solver. Unless you incorporate appropriate models, unless you calibrate your results with some experimental data, it's not trustworthy.
Okay, sir.
Hello.
Yeah, hi.
Yeah, good afternoon, sir.
Good afternoon.
Sir, actually, it's a nice session. So I have one question, sir. You have discussed in one of the slide about the calibration of the parameter.
Yes.
So there we cannot give the arbitrary value.
Yes, we cannot give arbitrary value.
Yeah. So that will take when will you give the arbitrary value, they can be treated as a garbage value. So my question is that, so till how much extent we can tune any parameters, like any percentage or something like that?
So it's nothing to do with the percentage or the absolute or relative error with the existing default values. Mm-hmm. So when you study about the physical phenomena, for instance, if you study about tunneling, when you are deriving the WKB approximation, or when you are kind of deriving things, for instance, the formulas for effective tunneling mass and all, then there are certain range of those tunneling mass which are physically plausible for electrons.
Okay.
So you have to take into account that physical phenomena and not exactly these default parameter values.
Okay. So, sir, this parameter value will be can we find from the papers or something? It will be written in the manuals.
Papers have some of these values. Yes.
That means range of the acceptable values.
See, range. So if it's within the same order of magnitude, I would say that safe limit is if it's within the same order of magnitude, it's perfectly fine. If it's 0.1 m0 is default, you are using 0.9 m0 is fine. But the moment you go to 5 m0 or 100 m0, you are violating that order of magnitude principle.
Yeah, definitely.
So then it becomes difficult. Yes.
Okay. Thank you, sir.
Okay. So any other question?
Thanks, Subham. It was a very nice presentation. Okay. And thanks for giving such a nice presentation and finding time from your busy schedule. Yeah. So thanks a lot.
Okay.
Any question from the audience? You can ask.
Yeah, any last minute questions? Any suggestions, any feedback? That will also be appreciated.
If you want, you can write in the chat box also.
Yeah. So there was a question, it is possible to solve fifth order differential equation. See, none of the physical phenomena follow fifth order differential equation as far as I understand. I mean, Poisson equation is the second order. So fifth order, I don't think it can even solve. Or, I cannot say that it cannot solve. Maybe with some numerical solver, people can even come up with a fifth order solver. But again, the resources and all will be quite huge in order to solve that equation. And the other thing is you can always approximate, fifth order differential equation to some lower order differential equation. So that is also something that people can do. Can we use this simulator for design of optical fiber? No. So TCAD simulators can only be used for device simulation. You can use it for simulation of solar cells and all if you want to go ahead with optics. But there are some dedicated simulation softwares when you want to go ahead for design of optical fibers and all. So I do not know much about those softwares, but at the same time, I would like to say that the inherent operation is again same. They will also be using or solving some kind of waveguide equations. That is what they will be doing. Okay, so is it possible to design 2D effects? I would say for the time being, people have shown some results, simulation results, even in transaction on electron devices for 2D effects. It is possible, but you need to have all the parameters for 2D materials available. For instance, the mobility. Also, I would say the conventional drift diffusion mechanism, it fails to kind of tell you the exact kind of formulation or the transport mechanism in these 2D effects. But you can approximate it. I mean, first level of approximation is fine. But if you want accurate simulation results, or if you say that whether if I simulate it in Centaurus, will it match with experimental data? Never. So we do not have enough material properties available right now for these 2D materials in order to incorporate that in Centaurus or any TCAD simulator. However, there are some TCAD simulators nowadays available in the market where they start from DFT level. So they take in the material, they do DFT calculations, and then they incorporate the effective transport mass in the valleys and all those things, and then they do device simulation. So there it is possible to design 2D effects. But in Centaurus, it is possible. I mean, you just give it as an input, and it will give you an output. But the validity of that output is very questionable. Any other question from the audience?
I think there is one more question, like, is it better than MATLAB?
Okay. So I would say yes, it's better than MATLAB because it's application specific. And it's quite user friendly, I would say. For instance, in MATLAB, you'll have to write the code for everything. For each step, you'll have to write a code. Here, you just have to specify the structure, you just have to include the model files, and then the simulation is done. In MATLAB, you'll have to write even the codes for those, physical models. So that way, it's difficult. It's better than MATLAB in terms of, computational resources. It takes less, and I would say ease of operation is there. So that way, since it's application specific, it's better than MATLAB. Okay. Any other query? All right.
Okay. Thanks, Shubham. Thank you again.